Well, given that it's midnight, I figure what better time to teach about some Laplace transformations than now, right? You know what I'm talking about. It's that math time. So let me kind of paint a picture here. So we're in chapter 7, and the topic for chapter 7 is what we call the Laplace transformation. And I'm gonna kind of show you what I'm talking about in just a second. I want to say that for most engineers, I asked a previous student of mine once, who was at Virginia Tech, I believe Virginia Tech, or he may have been in grad school by that time, but nevertheless, I asked, so what would you say to yourself back when you were at Lord Fairfax Community College with me? What would you have told your past self? And what he said is to pay more attention to Laplace transformations. And it is true because most engineering students will remember Laplace transformations, because they are an incredible time-saving technique. They have their pros for sure, some drawbacks as well, that I'll talk about here in just a little bit. But nevertheless, let me do this. Instead of trying to sell you on the why of a Laplace transformation, let me begin with the how, all right? And first, let's begin with the what is it. So let's note that, let's assume for a second that you have some function f of t. And the idea is you want to transform this function, right? And a special type of transformation, which we're going to call the Laplace transformation. So notice how the Laplace transformation is defined. So let's make it really simple. One of the things that we're going to be doing, and by the way, this is e to the negative st. It doesn't really show up as well with a stylus, but that's to the st. So let's make it really informal, but so the idea is we're going to take our f of t function, we are going to multiply it by e to the negative st, and then we're going to integrate that result from 0 to infinity. Okay, so no why, no yet. Let's just continue with the how. So what we're going to do is we'll just jump into an example. We're going to start really easy. Let's determine the Laplace transformation of the function, and let's make this function really easy where f of t is simply equal to 1. Right? So, and of course, for all t greater than or equal to 0. So in this case, f of t is actually just equal to a constant 1. Okay, well, again, looking at the definition of the Laplace transformation, you can just imagine that I'm inserting a 1 in here for your f of t function. And let's go ahead and write that out. So that would be the integral. First, let me go ahead and write it. So what you're going to see in just a second is the notation for Laplace transformation is either going to look like this or like this f of s, and you'll understand this s in just a second. Okay, so let's go ahead and define it. So it's the integral from 0 to infinity of e to the negative st multiplied by, and of course, f of t in this case is just 1. And we're going to integrate that with respect to t. Now, first off, we're going to have to go back in time a little bit, back to second semester calculus, and do you recall how to tackle what we call indefinite, or I'm sorry, improper integrals, right? So improper integrals, in this case we're looking at the form, say 0 to infinity. Now, the way that we defined that back in Calculus 2 is we are going to, and since you can think of it like you're trying, this is definite integration, right? Just to kind of paint a picture for you. This is definite integration, but notice that we are trying, you could think of it, we're trying to find the area under the derivative as x goes to infinity, right? From 0 to infinity. So and we want to be able to know if does that actually converge upon some actual area, or does it diverge, meaning that you have an infinite area. Again, just think about it for a quick second. Listen, if I want to find the area, say, under a curve like this, now I can, the way we started with the definite integration is we would try to bound this curve, right? In other words, you can't talk about area unless you can box something in, right? Like there has to be, you would think about it, at least back in Calc 1, you would have to think about it as, above the x-axis from, x is 0 to x is 2 or something like that, and then under the curve f. In that way, you see how now you've actually boxed in this portion of this region that you want to find the area of. Only now you can think of it as we're not actually bounding the function, right? We're letting x go to infinity. So it's very clever, the technique here. So the way we're going to do it is we're going to replace that infinity symbol with some arbitrary constant, right? So I will use the terminology of our book, which they use n. Back in Calc 2, we probably would have used b or a, something like that. So again, this n value is some, you can think of it as some value on the x-axis or the t-axis, depending on on which variables you're using. But nevertheless, we then take the limit of that arbitrary constant as it goes to infinity. So that is how we're going to be evaluating these Laplace transformations. Okay, so let's go ahead and do that right now. So to do this, we want to be able to take the limit as n goes to infinity, and we're going to be integrating from 0 to n of just e to the negative st dt. All right, now this is a fairly easy integration. We're just going to define u to be negative st, and of course du is just going to be it's hard to make, I have a hard enough time making my s's in 5, or distinguishing between s's and 5s with a pencil, but it's going to be even harder with a stylus, so I'm going to do my best. But if you take the derivative of u with respect to t, you just get negative s dt. All right, so at this stage, I can insert a u here for negative st, but the problem is, of course, I'm going to want a du here, but I think you realize I'm missing the negative s. But that's okay, because we're treating s like a constant. So I can, in other words, look, I can multiply by negative s right here, as long as I'm willing to divide by negative 1 over s. So now my integrand fits perfectly to do this u substitution. So what does that look like? So now I got the limit with n going to infinity, negative 1 over s. And now we're integrating from 0 to n. And there it is. We just have e to the u du. Okay, so we're going to go ahead and evaluate, of course, just like the derivative of e to the x is e to the x, the integral of e to the x is e to the x. So the integral of e to the u is just e to the u. Of course, it would be e to the u plus c, but we know that the c's disappear when we're doing definite integration. So negative 1 over s, and ready. And so right now I'm just going to integrate e to the u, which I get e to the u. But instead of doing another step, I'm going to go ahead and put that negative st back in here for u. So negative st. All right, so at that point, let's see, and then we want to go ahead and set this up. Now we're still going from 0 to n. All right, at this stage, you probably can anticipate where this is going. It's just, now it's the f of n minus f of 0. Okay, so we still got to take that limit, but we'll do that in just a second. So we're going to be, now I'm fairly positive that you already know this, but look, if you integrate with respect to t, you want to make sure you are, or I'll write it here, you're subbing back in for t. So all that's going to happen right now is it's going to be plugging in n for t, plugging in 0 for t. Let's see what that looks like. So now I got the limit as n approaches infinity of, let's go ahead and distribute this out. So this would be negative, what do we got? E to the negative s n over s. Okay, so all I've done is I went ahead and distributed that 1 over s, and I inserted a n here for t. Okay, so then remember that you have a negative here, and you have a negative here. So minus f of 0, that's going to end up being minus negative, right? So we're going to end up having plus. And of course, I'll go ahead and, just so you have some decent notes, that's going to be e to the negative, it's just going to be e to the 0, right? I mean, if you plug 0 in here for t, negative s times 0 is just 0. So e to the 0, which is going to be 1, but it's e to the 0 over s. All right, so far so good, right? Just all we did was distribute that 1 over s. Okay, so now at this stage, I'm going to do a couple things in one step here. So the idea of the negative exponents, if you've had me for a while, you've heard me harp on try not to keep negative exponents, because what I'm going to, with this, I'm going to move this from numerator to denominator, so I don't have that negative exponent. And then the limit becomes really easy, right? I understand that if you saw that limit, you started thinking, oh my gosh, are we going to do delta epsilon again or something of that nature, right? But no, these are going to be pretty easy limits. So I'm going to just move this e to the negative sn from numerator to denominator, and the reason I do that is because I don't want that negative exponent. And this is going to be plus e to the 0 is 1, so it's just 1 over s. All right, and now at this stage, all you have to understand is, I don't know what it means to plug infinity in for n, okay? But for all intents and purposes, we can think of that as what we're doing. But listen, does it make sense that if you have $100 and you divide it up amongst, I don't know, 10 friends, then everyone gets $10. But if you have $100 and you divide it up amongst 100 friends, then everyone gets $1. Right? As that denominator gets larger, everyone's getting less money, correct? So if you start to divide a constant up an infinite amount of ways, well, then no one's going to get any money. So if you want to think of it as subbing an infinity here, then that's just e to the s times infinity. That's just 1 over infinity. So the limit, no, I'm not even going to write it because I think you see it. This is going to become 0 plus 1 over s, right? The limit has to do with n. So again, I'm going to use the language of plugging in infinity. You only plug it in for anywhere there's a value of n. See, this 1 over s is not affected by that limit because there's no n in the 1 over s, right? So anyway, if you take $1 and you divide it up an infinite amount of ways, then, well, nobody gets any money. So what you're left with is just 1 over s, and that indeed is the Laplace transformation. That is your answer. That's, of course, the domain is s has to be greater than 0. All right, now, we are going to, again, I completely understand that I have not really talked to you even in the slightest as to what this transformation does, and nor am I going to for a little bit. We're going to practice the how for a while, and then I'll come back and I'll try to show you why this is something you might want to, something, not only do you just want to be able to do it for a test, but something you want to keep in your pocket as you go to your four-year schools, etc. So let's take a note at something really quickly. So I'm going to box in this answer. So this is your Laplace transformation. And I want to point out some things. So do you notice that we end up with a function of s? So the Laplace transformation, and you'll see this more in just a second, but it takes you from a t domain to an s domain. In other words, it used to be our function was defined in terms of t, but it undergoes this transformation, and now it's defined in terms of s. That's interesting, but let's just continue the transformation. So I think the best thing to do is to grab this whole thing and bring it with me. So let's see how this goes. All right, so let's do a few more examples. So the second example. Let me write the question in its entirety so that you can see the way it would look like on a quiz or on a test. But something like, let's say, determine. This time, instead of using the symbol, I'll just say determine the Laplace transform. of, and now I'm going to define a function for you. Let's say f of t is equal to e to the, and this is an a t. So f of t is equal to e to the at, and let's go ahead and say a is just some constant. So obviously non-zero constant. All right. So we have our function, and let's go ahead and start to set up the Laplace transformation. So I'm going to be going right here, since I know that I'm going to be integrating from 0 to infinity anyway. So let's just go ahead and start setting that up. So we are going to be looking at the limit with n moving to infinity, 0 to n. All right. So e to the negative st, everything is right from this definition. Only now we're going to be plugging this e to the at in here for this function f of t. All right. So multiplied by e to the at, and we're going to be integrating that with respect to t. All right. So it's worth taking a second and manipulating this integrand, right? So, I mean, if you have e to the negative st multiplied by e to the at, right? Look, if this is like if you have x squared multiplied by x cubed. You and I know that's x to the power of 2 plus 3, right? But it's not like that only works for variables. If you have the same base, then when you multiply them, you can add their exponents. So you can see this becomes e to the negative st plus at, right? E to the negative st plus at. And then all I'm going to do is I'm going to factor out a t. In fact, I think I'm going to factor out a negative t. So that's equal to e to the negative t. And that'll just leave me with s minus a. All right. So that little bit of work up front, and now that's going to be the integrand that we are going to be integrating with respect to t. All right, I'll go ahead and start to insert this. E to the negative t times s minus a dt. Okay, so again, we're going to go ahead and the integration here is not bad. We're just going to let u be defined as negative t multiplied by s minus a. And as long as you can keep in mind that we are treating s, and of course a is a constant, then, I mean, just like, look, if u were to equal some constant to t, then du is equal to just 2. Well, this s minus a, I don't know what they are, but they are constants. So when I take du, the derivative of negative t is negative 1. And of course, I still have this s minus a left over. Again, if that confuses you at all, just think of it, if I had u is equal to negative 2t, then wouldn't du be equal to negative 2 dt? Well, you can see, I'll write dt here in just a second, but you can see the negative here, and then instead of having a 2, we just have an s minus a because they are constants. Okay. So, and that is dt. All right, so this allows me to do the u substitution. Now, what you're going to notice is, so I will be able to make this entire exponent u, but in order to make this dt du, I am going to have to manipulate that integrand, right? So I'm going to have to multiply and divide by the thing that I'm missing. I'm missing this negative s times s minus a. Let's go ahead and write that. So we got the limit with n moving to infinity. And here it is. So I need to multiply and divide by negative, so this is 1 over negative s minus a. Now, of course, I could distribute that negative symbol, but right now I'm being lazy. And we want to go from 0 to n. And now this is going to be EU. And all I'm going to do is go ahead and write that negative s, let's say negative times s minus a here. And as of right now, it's dt. So you can see that once I multiply and divide by this negative multiplied from a negative of s minus a, then I can insert du. All right, so easy enough. So let me go ahead and do that. And so I'm going to, if you integrate e to the u, it's just e to the u, and then I'm going to back substitute. So that leaves me with the limit with n going to positive infinity, 1 over negative s minus a. And now I'm going to go ahead and integrate that. I'm going to integrate that, and I'm going to back substitute. So integral of e to the u is e to the u, and let me put that negative t times s minus a back in here. So negative t times s minus a. And of course, I'm going from 0 to n. All right, so far so good. You know at this point, it's a matter of f of n minus f of 0. So, okay. So again, just realize that the n is being plugged in for t, the 0 is being plugged in for t. And of course, always with improper integration, the last step is to evaluate the limit. So don't try to evaluate the limit yet. So here it is. So we're going to be taking the limit, n to infinity. And now let's go ahead and I'm going to, this is going to end up being e to the negative n times s minus a over negative s, that's the product of negative and s minus a. All right, so that's the first part. And then now I'm going to be plugging 0. And for t, of course, that's just going to be e to the 0, which is just 1. So again, I'm going to end up with a plus symbol. Just remember, it's easy. It's easy for me to forget too, but I have a negative symbol here and a negative symbol in my fundamental theorem of calculus. So that negative ends up being plus. So plus. Now plugging in 0, e to the 0 is just 1. And at that point, I just have s minus a. well, let me think here. Yeah, I'll go ahead and write it as s minus a. Of course, I hope that makes sense. You had minus f of 0, that would be minus 1 over negative s minus, negative 1 over, my sincere apologies, my stylus is dying on me, I think, negative s minus a. That's right, so it's f of 0, that's negative 1 over s minus a, basically times e to the 0. So that's where that double negative that you're seeing right here ends up just becoming this plus symbol. Okay. I understand for many of you, you just spot it right away, but for some, like little things like that can bother you, right? So notice that if I'm going to do this in one swoop here, if I move this to the denominator, which I would because it's a negative exponent, then do you see how when you evaluate the infinity here, and for n, that's again like dividing by infinity, right? So that ends up becoming 0 plus 1 over s minus a. And that is your Laplace transformation. So f of s is indeed equal to 1 over s minus a. All right, so I'm going to go ahead and call it quits for this video, and I will see you back in just a second.